Let me also throw in some verticals for the asymptotes. So I'm just showing a little bit of it. I have to put the vertical lines in one by one, and I'm not going to do that. Okay, so there you are. Unforgettable, right? You've never seen anything like it before. I think until you see tangent, there's nothing like it, right? There's nothing in the world like it. Cotangent, actually, is a lot like it. Let's look at that briefly. Not a whole lot to say about cotangent. Let me put them together. There you are. There's cotangent. There's tangent. Tangent. Cotangent. How come? Think about what cotangent is. It's just the other division. It's not sine over cosine, it's cosine over sine. And so everywhere the sine is 0, you're going to be dividing by 0, and that's not allowed. So I wanted to tell you about... Oh, I didn't have a slide for cotangent. Oh dear. Oh well. Maybe that would be good for you to sort out. I'll just say this though. Everything that we said for tangent applies. Right? You still get this period. Yeah, you don't quite get this anymore for the domain of cotangent. In fact, you can see it here, right? You can see what the domain is. You're not allowed to take the value 0, for instance. You're not allowed to take the value pi. Right? We've got the disconnect in the graph. Same thing at 2 pi, you got the disconnect. So it seems like the fix would be, not the fix, but the description of the domain for cotangent. I'm sorry, I'm pointing at things you can't see. So this stays if you're talking about cotangent. It's just the other division. Not really anything to consider there. The domain for cotangent, you can kind of see it, right? It's just before you. You can't take the value 0. You can't take the value pi. You can't take the value 2 pi, and so on. Same thing out here. You can't take negative pi, and so on. So the description for the domain of tangent is very close to the description for the domain of cotangent. Just got to modify this ever so slightly. The principles are the same. Okay, any questions there? Please let me know if you have any questions there. Ah, yes, also, if you could type in here, if you haven't yet, please let me know by typing here. Alrighty. Good. So that is tangent. Let's look at the others. I'll be honest with you, these don't come up too often. Certainly not the graphs of these. But you should know what they are, and you should know why they look the way they look. This is a mathematics class after all. This is not facts memorizing class. Okay. Secant and cosecant. Oops. I've got a whole bunch of facts there. I don't think you have anything to memorize that you don't here that you don't already have memorized. You should memorize, should have memorized, for instance, that the period of sine is 2 pi, and the period of cosine is 2 pi. You should know that, and that's kind of it. Oh, sorry. And the other thing is that what is secant? What is cosecant? Everything you know about sine and cosine translates over. They describe this in full. once you recall that. So don't even look at that. This is 1 over cosine, and cosine has a certain period. So 1 over cosine, it's going to have the same period. There's no other consideration similar for that one. Sine has a certain period. So 1 over cosine, it's just 1 divided by a number. It'll have the same stamp width, if you will. Same period. Okay, for the domain of secant, it's this. Why? Because that's where cosine equals 0, and you can't divide by 0. Pi over 2 has cosine 0. Pi over 2 is 90 degrees. X-coordinate 0 there. And that's the end of the story. You get that again at 3 pi over 2. AKA when you have pi over 2 plus 1 pi. And so on, so on, so on. Similar for cosecant. You can't divide by 0, so everywhere sine is 0, it's not allowed. It's not in the domain. Where is sine 0? Think of the y-coordinates on the unit circle. Okay, sine of 0 is 0. And where's the next place it's 0? At 180. The angle there is pi. We said 0, we said pi. The next thing we would have said is 2 pi and 3 pi and 4 pi and so on. The integer copies of pi are not allowed for cosecant. I think the trickier one is the range. How do you know it's this range? And by the way, I'm not sure if you've seen this. Probably you've seen this before, but maybe it's been a while. I'll draw it for you. It means this collection of numbers. There's 0, there's 1, -1. And you do get that value. Also these. Phrased differently, what we're saying is, no matter what angle you ever consider, you will never get a secant of 1/2. It will never happen. Same for cosecant. No matter what angle you consider, you will never get a cosecant of 0. It will never happen. 0 is not in the range. So that's the more valuable way to think about the range of these guys. I think, what do I never get? I will never get anything between -1 and 1. Period. No matter what. No matter what angle we consider, this will never result in 1/2. This will never result in -1/2 or 0 or -1/3. None of that. Okay, the last thing that I want to tell you about these guys is how do you get your table of values? Let's have a little look. Maybe. So if you have a table of values for cosine, reciprocal them. And those are now your values of secant. So I've got a few memorized. Oops, and I should be consistent. Let me say t. So I know that when t is 0, cosine is 1. And the reciprocal of 1 is 1. This is your value for secant. And similar. pi over 6. Cosine is the x-coordinate, so you get square root of 3 over 2. So over here you'll have 2 over root 3. AKA 2 root 3 over 3. And so on. So you'll have 2 over root 2, aka 2 root 2 over 2, or just root 2. Anyway, at this point, you'd go get your trusty calculator, go get approximations for this, and now you have a table of values. T values, I don't want to say this, I know it doesn't say X, but X values, Y values. And that's the end of it. Now you have a graph. If you have enough points, you'll have a graph. Let us look at both cosine and secant. It's t. Now everywhere that this is 0, cosine, which is on screen, you'd be dividing by 0, and secant would be dividing by 0, and you don't want to do that. Let me mark those with vertical lines. So cosine of what is 0? Pi over 2. Okay, so phrase differently, I'm going to put a vertical line at every single x-intercept. At least a few. I'll do maybe 2 more. Let's make this nice. And this one too. So here's what you got to see. Here's the key to really getting why the graph is what it is. Just one by one, ask yourself what the reciprocal of this number is, this y value. Whatever the reciprocal of that is, that's your value for secant. Right? You're looking at a picture, the dashed line there, the curve is cosine. So the reciprocal of this y value is the y value of the secant. So reciprocal of 1, for instance, is 1. And the reciprocal of 1/2 is 2, right? 1 over 1/2 is 2. And the reciprocal of this, oh boy, this is kind of small. The y value is kind of small. The reciprocal will be big. Over here, the y value is smaller, so that the reciprocal will be bigger. As you really get in there, the y values are minuscule. Therefore, the reciprocals will be giants. Also, think about the negatives. So for instance, here, the y value is negative, but it's small. It's very tiny. The reciprocal will be negative and giant. That's the whole idea. You can't cross these dotted lines. The function's not defined there. You can't divide by 0. Okay, I think I've said everything I need to say. Here is the graph of secant. And we're not at all surprised. What else could it be? It has to be the reciprocals of the y values of the cosine. Sometimes the cosine is relatively big. The biggest it is ever is 1, and the reciprocal of 1 is 1. So they touch, they meet. And as you move away from the mountain, the y value is smaller, so the reciprocal will be bigger. Okay, and the far end of cosine at -1, totally the same thing. It's just now you're dealing with negatives. The reciprocal of 1 is 1. And as you consider nearby y values, the y values are less far away from 0, so the reciprocals are huge, or rather they get huge. The closer you get to 0, the more giant the reciprocal becomes. So what else could it be, right? So you get this shape. And in fact, let me just show you the shape. No cosine. Okay, there you are. It's not a requirement to draw these dotted lines. I hope that they're not distracting. There it is. That is secant. You don't really graph it without first thinking of cosine, though. That's the instrument. Use cosine. So if you ever have to plot these things, you want to plot the cosine version lightly. Wherever you have x-intercepts of cosine, you get these things. Don't cross them. At the mountaintops, they meet. At the valleys, they meet. And you draw this U shape. And that's about as much detail as you'd ever have to be aware of. Again, these don't come up that often in future studies, but you should be aware of them. It's par for the course. Do you guys have any questions so far? Please let me know if you do. So yeah, I'm not going to bother too much more here. I do want to show you the other one, cosecant. I'm just going to cut to the chase, though. There you are. Where does this come from? It comes from... Wait, I'm sorry, I meant to do the other one. Where does this come from? It's a reciprocal of sine. So everywhere sine is 0, you have a vertical asymptote. Sine of 0 is 0. Where are some others? Pi, right? Let me throw that away and show you where it comes from. Okay, so that's it. It's nothing else to say. It's just reciprocals. Plotting the reciprocals of the functions that you know well. Okay, so here, oh yes, I wanted to say one thing here and then we'll take our break, I think. Yeah, we go on to a new section. You can't see what I'm doing. Okay, so good, and this is the last thing I'll say before the break. I just want to say why this is true. You see, and I say this many times, you don't want to memorize things if you don't have to. You don't have to memorize these. I would encourage you to not memorize these. I'd encourage you to memorize what they are. You should know what tangent is in terms of sine and cosine, and same for the others. And if you write that in, your existing knowledge about sine and cosine will tell you these things for free. So you don't have to save brain space for these guys. Let me put that, put down what I mean. Just write it out. It's always sine over cosine of the angle exactly as it is. And at this point, you do have to remember, what does sine do? What does cosine do? We'll give it a negative. So the fancy term is that sine is an odd function. Cosine is an even function. Odd functions do this with negatives in their as their input. Even functions do this. And that can be rewritten. So it's like that for all of them. I'm not going to bother with the others, so leave that to you as an exercise. It's a good exercise perhaps the one that's most interesting is the one that's different. This third one, it doesn't have a negative. How come? You want to do something like this, just say it, secant, but you have to say what secant is. You need to say it. So you say secant negative theta with parentheses. Just copy that in. Then you know something about cosine. Cosine is even, therefore it doesn't care about negatives. Kind of ignores them. Cool. I think my Zoom disconnected. Okay. Oops. Yeah, I hope I wasn't gone too long. My Zoom just disconnected and came back. I hope I wasn't gone long. Okay, we need the time, and we'll take a short break. Okay, so let's see. Yeah, so let me show you one that can't be undone. This one can be undone. As I've written out this table, you can undo the table. The inverse exists, we say. Let me give you one that cannot be undone, that you are familiar with. The square root function. The square function has no inverse. I'll show you. Hope you don't mind my going back and forth between notations, function notation, y equals, if you like, think here, x is x squared. Okay, and here we are. I know that if I square negative 2, I get 4. If I square this, I get 1. If I square this, I get 0. Square. Uh-oh, I'm starting to see repeats in the y values. See what I mean? I can't undo it. I don't know what to put. This would be the inverse. I'm not gonna, I don't want to describe it with too many symbols, but you see what I mean? I don't know what to put here. Should that be a negative 2 or a positive 2? It's not, they're both good, right? I mean, they both seem fine. The fact that I cannot pick one and it is not determined for me is what makes this not have an inverse, the square function. So that's an important idea that you need to come to terms with. Not every function can be inverted. There are things one can do, and then you can talk about inverses, but at some point you have to make a choice. Do I want... Let me show you with Desmos what I mean. Too. It's just going to be a rephrasing of this, but with pictures. Hold on here. I need to put... It's not clear. Not clear what should go here. Okay, so yeah, let's look at the square. The parabola, by the way. Nothing more than that. Oh, cool. I'll use function notation. You know this one. Okay. Maybe you've heard of the square root function. When you take a square root, though, you do have to be careful with the plus and minus sign, right? Do you see how I can't plot like one function and can I just show you? Yeah, so like maybe you've heard of the square root, right? So I put that one in. Call it g. See what what's lacking? Like, it's not a, it's not the mirror reflection that it should be. When you have inverse functions, they're mirrored across the diagonal like that. You can kind of see like imagine folding along the diagonal, and there's no overlap. At least it's not a complete overlap. You have some overlap. Let me complete the picture, and I hope you really see. Oh man, yeah, that's not a function. You can't even talk about that. Call it H. There we go. Let's make this look nice. That's more like it. Here's the problem, though. Red is the one that's like a sideways U. That's not a function. So you can't even talk about it. See, it has no inverse. There's no one inverse function for the square root. Sorry, for the square. See, not a function. So sine does that too, unfortunately. Same for the other trig functions. Here's the fix. I'll show you. Just do part of it. Don't do the whole thing. Don't invert the whole thing. You can't do the whole thing. If you consider both negatives and positives, you could repeat y values. And if you have repeat y values, it's not clear how to undo the 4. It's not clear. Should it be a -2 or a +2? And we don't want that. The choice. However, if you restrict this, if you're willing to look at just a piece of this you can invert. Now you have to be creative and you have to figure out, oh, how should I invert how should I restrict this so I can invert it? Here's one way. Let's look at what side? I'm going to look at the left side. It's less 0. Okay, there you are. This can be inverted. Its inverse will look like this. It'll look like the mirror image across the diagonal. Can you see the mirror image? It'll look, well, I'll just show it to you. It's right there. So if you turn your head right to line up with the diagonal, it should be symmetric on the left and the right. So the dashed line acts as a mirror. The dotted line is the reflection across the mirror of this solid curve. Okay. Let's look at the other one, the other side, maybe. The positive side does have an inverse. Notice there is no repeat y values on anything that's on that right half of the parabola. There's no repeat y values. You see, that's the issue here. There's repeat y values. If you say the output is 10, I won't know what the input was that gave you 10. That's the issue. It's not clear what that would be. But if you were willing to look at just one piece, maybe the right-hand piece, like that, now we're talking. That does have an inverse. If you say the output is 10, I know what the input has to be. It has to be the square root of 10, positive. Graphically, there's this nice property about symmetry, across this mirror. Okay, so that's the idea. Sine doesn't do that, right? Let's look at sine. Uh-oh, you have too many choices, right? If you say, here, pose the question. Pose the question again. If you know that the angle theta or the number theta has this sign, it's not clear, but what theta is, I'll show you. So 0.1 is a little bit up, right? So see, There's many. This one, that one, and there's as many as you want. So that's the issue. Aha, so what do we do to fix it? We do exactly what we did for the problem. Just look at a piece. The piece to look at is up to you. For instance, this would work well. People don't do it, but I just wanted to show you that it would work well. I'm going to do from negative 3 pi on 2, no, negative 5 pi on 2, till negative pi on 2. Doesn't quite work, does it? I went too far. See, I still have these repeat y values, and when you have repeat y values, it's not clear how to undo it. Okay, so I've gone a little too far. Maybe I can do 3. All right. There's no repeat y values here. And you could invert this now. It's weird, but you can invert this one. People don't. They invert this other one. I'll show you now. With symmetry about the origin. So a little bit to the left, and a little bit to the right. This is the one that people invert for no good reason other than that it's nicely located in the middle. This is invertible. There's no repeat y values. So there's a table here. Maybe I can even show something like that to you. There's a table here, okay? There's no repeat y values. So if you have a y value, the x value is determinable and there's no choice to make. That's a good thing. So that in that case you say this function is invertible. There's no repeat y values. Maybe you've heard this expression, this term, one-to-one function. Okay. This is that. Right? You say that this is one-to-one because there's no repeat y values. One x value means there's exactly one y value partnered with it. No doubles, none of that. Again, no repeat y values. By the way, the problem would be it's not one-to-one. It's not one-to-one. You say it's 2-to-1 if you're going to say anything. In any case, it's not 1-to-1, therefore it's not invertible because there's repeat y values, and the repeat y values make it so you don't know what that should be. It could be one of two things, possibly, and they're both fine, right? Well, not for a function. No, they're not. Okay, so that's what we do. We invert this little piece of the sine function. Here's the full sine function. All right, so that's what you do. You just invert a little piece of it. It has a name. So probably should do one thing at a time. Oh yes, I thought this was good food for thought. So one approach to inverting a function is just to do this, but you would want a gigantic list, right? A gigantic list of values of sine for a variety of angles. And then you would do what I did. You would just go like this. You'd reflect the columns, right? And there you are, all done. This is good. It works. It totally works, but it is not very efficient. We have better tools now. We should use them. Okay, cool. So yeah, it's time now. Yeah, so you want to memorize this. I think when you're first starting out with inverse functions, it's just plain weird. I'm sorry. I'm sorry. It's kind of normal to feel that way. Like, this is just bizarre. You know, what I'm seeing doesn't make any sense. It's unfortunately normal. And I hate saying this, but you want to memorize this one and also this one. I promise you, it will save you some trouble. You want to make a flashcard for these. Yeah, for sure. Okay, let's show them to you. Maybe one at a time. First one is sine inverse. Unfortunately, Desmos, I think, cannot deal with the -1. This -1. So there's a nickname. There's a nickname for the sine inverse function. I'm gonna try the -1. Maybe I can be proven wrong. No idea if this will work. I doubt it. It worked. I wasn't expecting that. Okay, now you really see it, right? The symmetry across the diagonal. Ooh, that's nice. Cool, right? So that little piece of sine is invertible. In fact, many pieces are invertible, but this is just the one that is in common use. This piece of sine that is a little to the right of the origin, a little to the left of the origin, that's what we invert. Just that little piece, not the whole thing, because you can't. Just that little piece is, oops, I don't want all that. That little piece is invertible. To see it, go like this, and then everything that's on the left. Oh my goodness, I'm not showing you what I'm pointing at. My apologies. There we are. Where did I leave off? Oh dear. Okay, let's start here. Sine is not invertible. You have repeat y values. The fix is don't use the entire sine. Use a little piece of it. It's common to use this piece there. But you could use the other ones. Anyway, people use this one. To see the inverse, I'm going to reflect across the diagonal, y equals x. This has the effect of going like that to your columns. And here it is. So everything that's that way in the mirror reflection will be over here. Like that. So this one has a name. I'm going to memorize what this looks like too. This one is called inverse sine. I think the more correct name would be arc sine. It's a nickname. It's no more. So you might see both. That's exactly what this is. There. That there. You might say sine inverse. You might say arc sine. People only say arc sine just to avoid this negative one. The negative one is suggestive of a reciprocal, and that's not a good thing. Unfortunately, that symbol is with us, and people are going to use it. So you want to recognize both forms of saying this idea, the inverse sine, the arc sine. Think of these as being synonyms. Okie dokie. Cool. Yeah, so you want to memorize that, and this one and this one. I think I'll come back to these as we need them. Oh yes, I wanted to show you some of the others, right? You've got other functions, cosine inverse, tangent inverse. Let's look at them. Oops. But it would be good if you could see what I was doing. Not yet. Okay, here you are. All right, there's a problem. You can't invert this. If I tell you a y value, there's no way to know one x value that went with it. You'd have a range of choices, and for talking about functions, that's not a good thing. For a function, you get one output for every input. So the inverse function will see the outputs of cosine as inputs, and then the inputs of cosine as the outputs of the inverse. So it's a very fancy way to say inputs become outputs and the other way around for the inverse function. Okay, anyway, you can't invert this, so we don't. So what we do is we take a piece of it. Now, you can take any piece that you want so long as there are no repeat y values. So let's try something similar as we tried for sine. For sine, look here, look here, look here. Oops, not there, look here. For sine, this was the restriction that we made. I mean, you can see below, it's not the same. But let's just pretend we didn't know that. I want you to see it, why this doesn't work. Pick exactly the same. See the issue? You got repeat y values here. If I tell you the y value is 1/2, it's not clear what the input was that gave you 1/2. You could have said this one. You could have said, sorry, maybe I'm putting it the wrong way, in the wrong place. You could have said this approximately. Could have said this approximately. It's more like right here, right? So you don't want a choice. You get repeat y values, that gives you a choice, and that's not good for talking about functions, inverse functions. It doesn't work that way. What we do is make a restriction. Not this one, because obviously it doesn't work. The one that people use is this one here. There's no repeats. It does describe cosine. You just have to like reflect it, stamp the reflections right throughout. Okay, so this is the invertible function that we all use. It's a part of cosine. It's not cosine. No one's saying it's cosine, but it is a restricted form of cosine, the function, and it's invertible. So, phrase, just again, because it's just so important. If you knew any of the y values here, anyway, if you knew any of the y values here, there will not be two x values for that y value. There's only going to be one. And therefore, if you know one of the y values, any of them, you'll know the x value that it came from, if you're looking at this restriction. But that's not the case here. If you know one of the y values on this cosine curve, that does not guarantee what the x value was. In fact, you even see one right here, right? If I tell you the y value, the cosine of my angle is 0.5403, that thing, it will be clear. Did it come from the input -1 or +1? So you don't want that. If you have that, you don't have a function. So what we do is we make a restriction. There you are. Okay. This can be inverted. Its inverse has a name. People call it inverse cosine. People also call it arc cosine. Here we are. And there they are together. Graphically, they're related by a reflection. Kind of cool, right? I mean, it looks nice, right? Looks like art. Cool. Now let's see it by itself. Okay, it's another one that you want to memorize the look of. So here, notice it doesn't go leftward and rightward forever. It doesn't go up and down forever. So the domain is not all real numbers. The range is not all real numbers for the one that's showing. Same thing here. The domain is not all real numbers. The domain is only, for this restriction, from 0 till pi. And the ranges, those are the y values that you see, the range is the same range as the non-restricted version. The range goes from -1 till 1, including -1 and 1. Okay. All right, there's the inverse. Oh yes, also you can see it as arc cos. Here's how you write it down. Arc cos like that. Okay, the last one is tangent. You can't invert this. There's repeat y values. We're hopeless. Can't invert anything. What we do is you pick one of these pieces, restrict yourself to that piece only, and now your table of values for that restriction will have no repeats in the y's. Therefore, you can trade the columns and you've got yourself a function. Here's the restriction that people use. For simplicity's sake, they like the The one that's chosen is the one that's nearest the origin. This piece here in the middle. Okay, where are you restricted from? There to there. Wait a minute, I know what that is. I know where those places are. That's where cosine is 0. That happens at negative pi over 2, and so on. Okay, so think about the period of tangent. Okay, let's put that in. So let me do this. There, this equals. There you are. That's just one of these. It's just that one. We don't have to use this one. There's nothing wrong with using this one, but no one does it. I'll show it to you. You could do this. There's nothing wrong with that. It's just that people don't use this one because it's, why did you pick that one? You know, why didn't you pick the one on the left? It's just not really natural, right? It's not as natural as the one that's, you know, dead center. Okay. Anyway, the inverse exists for this piece. I'm not going to work with that one. No, I'm going to work with the one that everyone works with. Everyone works with this one right there. And there is an inverse here. So just one more time, because it's just so important. You have a table of values. There's no repeats in the y's whatsoever. You can extend this table as long as you want, and there will be no repeats in the y's. Therefore, you can invert and you get a function. Or rather, you can trade them and you get a function. Yeah, you can invert the x and y's and you get a function. Okie dokie. And it's called arctan, or tan inverse, however you want to call it. Oops. There it is. Get this out of here. Okay. All right. So that's what they are. And we want to be able to use them. We want to be able to use, have our calculators use them. So we'll do some of that now. And I can't emphasize enough how important this slide is it will help you make sense of the things that your calculator tells you. The calculator is not going to tell you the full story because it can't. It doesn't, again, it can't invert. It can't invert this. Right, we can't. But sometimes you will need to think about angles in quadrant 3. And you want an inverse, but you want the angle to be in quadrant 3. So that is, you want to think of an angle with a particular tangent, but for some reason you need it to be in quadrant 3. Your calculator cannot help you. Your calculator cannot help you. So you have to fill in the blanks. You're going to have to use what your calculator does tell you, and then move your angle to quadrant 3 accordingly. Okay, so that's the kind of the whole picture there. If your head is spinning, I think examples will help. Let's get some examples on the paper. Oh yes, things you should know. I think I'll just leave that there. Yeah, and I told you about the nicknames. Cool, so I just leave that there. Let's get some examples out of the way. There's some questions, please let me know. I'm about to get carried away in examples. Oops, can't see. Let's do a bunch. really want you to make sense of it. It's not random symbols that have no meaning whatsoever. There is a very specific meaning to these symbols. The key, oops, not that, that's too big. The key is here, particular right there. You want to see this as an angle. And that's in contrast with this, which you do not. I'm just going to pick an angle in there. This is not an angle. That's an angle right there. Pi over 2 is an angle. You can think of it as an angle. This is a number between 0 and 1. You may safely think of it as y over r. It's a number. Y is a number. R is a number. It's a division of numbers. That's an angle in there. This is a number. Y over r. It's the other way around now. That is the y over r part. This is an angle. See, that's kind of weird the first time you encountered it. Okay, so first things first. I don't think it's a bad idea. Let's see what our calculator tells us. Clear, clear, clear. Notice I'm in radian. I don't know if my calculator is going to tell me the exact form. Let's see. I don't know how to do that. How do you do that? Uh-oh. I don't know how to do that. I don't think I have a calculator. I'm not going to use it. Oh, okay. Let's just think. Let's use what's in front of us, and we'll write it out. Okay, so it is an angle. Oops, angle. Whose sine is 1/2. Can you think of any angles that have sine 1/2? Sure. I can think of many. Sine 1/2, that will happen in quadrant 1. Right there. Well, let me think. So it's the y coordinate. Yeah, so you get one right here. Pi on 6, right? It gives you this point on your unit circle. Yeah, I've heard of that one too. Thank you for the reference. I didn't know what it was called. Yeah, I can't say that I've used it, so I can't vouch for it much. Yeah, I've heard good things about it. Photomath is it's really amazing what it can do. I think you can use your smartphone. You just hold it up to, I want to say, to anything, and it'll kind of read your mind. Yeah, it's a nice app. It's still good to know how things work, though. You definitely want to be comfortable with this stuff right here. Like, I feel like too many students go through their math education without a solid understanding of what the inverse trig functions do and how they do what they do. It's so weird because those functions are so weird because in order to even talk about them, you have to do this restriction thing. You have to say, this doesn't work. I need just a little piece. And if I have a little piece, now we're talking. And this little piece that I happen to like, because everyone else likes it, this one does have the ability to switch the columns, and you still get a function. That one I will give it a special name. I'll call this inverse function the inverse of sine. People also call it arcsine. Yeah, good. Thank you for the reference, Yvette. Okie dokie. So, have no fear, okay? Here's how to have no fear. View it as an angle. An angle with a specific property. That's one. But here's others, though. See, and this is the issue. This is the problem. Which one is it? Can't be both. Oops, sorry. Can't be both. Oops, let me draw the angle. It's not both. It can't be both. See, this is one thing. This is one thing. It's not two things. In mathematics, you write one thing down, there is only one thing down. There's not two possible meanings. That would not be clear. And we don't do that in mathematics. We are ultra clear. There's no ambiguity whatsoever. And so you see, like I hope the story is coming full circle now. Like that's the issue. You want this to have meaning, and for this to have meaning, there cannot be two things, or three things, or four things. There had better be only one thing. And you see the issue? I found you an angle that has sine 1/2, and I found you another angle that has sine 1/2, and it can't be both. It can only be one. So we have taken this choice. It will refer to these angles, the ones that are to the left of 0 and to the right of 0. Let's next. So I think you should do one of two things. You should memorize this word for word, or recreate the argument from the beginning in your mind. This one. This one. Okay. And then, this is invertible and blah, blah, blah. Cool. Okie dokie. So what do we do? Let's go back to the exercise. All right, so what do we do? There's a little more to say. Okay. So there's no choice anymore. I gave you two that are good. These both have sine positive 1/2. This angle and that angle. But we have made this choice where we do a particular restriction, and the particular restriction we do is this one. There's no choice anymore. I can find you an angle that has sine 1/2. Let me indicate it. Whatever that is. Yeah, I don't know what it is. Let me mark it a little bit better. Cool. I just found it for you. It's pi/6. I mean, there's many, but for this restriction, there's only one. There's only one intersection, right? So if you tell me the y value, I can tell you the x value on this one. I can't do it on regular sine. Again, it's not invertible. Right? I can't do it. There's too many intersections here. If I tell you y value, there's no one x value that did it, at least not on the full version. But if you look at the restriction, now we're talking. This you can invert. You say the y value, I could find the x value for you. I just kind of look down, right? I'll find the intersection, I'll just look down. Cool. So that's the full story. All done. Check it out. We're done here. That's nothing to it, right? But I'm sorry, there's nothing to write down, but there's a whole lot of thoughts you have to go through. There's like a whole story here. It's a very long story too, and we're done. Okay, we're good. Check it out. It's not that one. It's just plain old pi/6. Oops, I move that out of your way. How's that? Nothing to it, right? Oh, sort of. I mean, no. There's a lot to it. Nothing could be farther from the truth. There's so much to it. Oh, it's overwhelming. You know, the machinery that we needed to give this meaning. I don't know if you can tell I love this stuff. It's so cool. It's like we're hopeless until we do the restriction. Think back to here. No, not really. If you know the sine, not really. You don't really know what the theta was. There's infinitely many. However, there is only one acute angle that has that particular sine value, and that's always true. Unfortunately, for acute angles, so between 0 and 98 degrees, every single sine is positive. But that's not always the case. You know, there are other angles that have negative sine, and so that's why we restrict the way we do. That's why we use this restriction. This one right here. This one right here. Okay. Okie dokie. Let's get a few more out of the way. I think you'll. I hope it'll start to click if you see a bunch. Let's do that. Okay, and up next. Okay, so what's the meaning? In fact, can I show it to you first? I'll say it while I get Desmos out. View it as an angle. Okay. An angle whose sine is negative root 2 over 2. There's many. What do you mean an angle? There's so many. But there's only one that lives in the restriction of the domain. Okay. Now it's not vague. Now it is, there's only one such angle. Let's go see it. Alrighty, I will plot the horizontal line, negative root 2 on 2. Oops. Okay, there's only one intersection. I can tell you the angle that has this sine, negative square root of 2 over 2. It looks like it's that. So what are you? Whatever that is. I think that's pi over 4, but negative. Let's see. So that's it. That's the end of the story. Negative pi over 4 is a clockwise 45-degree rotation, and it is an angle, and its sine is this, and that angle is somewhere in here. Negative pi over 4 is, well, it's negative, and it's less, it's closer to 0 than negative pi over 2 is. Oh, you kind of see it right there, right? Negative pi over 2 is there, negative pi over 4 is there. Okie dokie. All done. So, also, I hope you're starting to believe me, like, how useful memorizing this is. This right here. You will have a lot less trouble working with these if you can memorize where the angle has to live. And the angle has to live in these places because of choices that others have made before us, and that's just what it is. Okie dokie. Here you are. That's all there is to it. You know what I mean. There's a lot to it, but there's no calculation to do. It's just, oh, wait a minute, what does this mean? Where does this angle have to be? It has to be in quadrant. I'm allowed to go from negative pi over 2 to positive pi over 2. That's quadrant 4 or 1. Okay, let's look at more. So again, you want to see an angle? Always you want to see an angle when you see this little symbol? The whole thing is an angle. And when I was learning this myself, I thought this was really helpful. I wrote down every single time. This is an angle, theta, blah, 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 blah. Whose sine, oh, sorry, cosine. Whose cosine is this. That angle lives in, what does my slide say? 0 to pi. Phrased differently. It's an angle theta whose cosine is this. That is in quadrant 1 or 2. Is that clear why it's quadrant 1 or 2? Because when you start at 0, at angle 0, until you get to pi over 2, you're in quadrant 1. And then when you get as far as pi, now you're now in quadrant 2. That's why. Anyway, look, the cosine is negative, so it's got to be the quadrant 2 one. Okie dokie, here we are. So I'm thinking, wait, what angle has this cosine? So maybe I'm thinking about quadrant 1, a little easier for me. Then I'll just think about the reference angle, kind of move it over. So I want -3, so that's this one. That's angle pi over 6 in quadrant 1. But I want the reference to be pi over 6 in quadrant 2. That means I should take 5 pi over 6, right? Here, let me draw the picture too. Wait, I don't need that. I already drew it. It's right here. Cosine. 5 pi over 6 is the angle that has that cosine in quadrant 2. Okay, cool. Can we do one more?